Swayam Prabha. Digital India. Educated India.
So we have a simply supported beam, and we have looked at this example using the method of sections. We have a simply supported beam P as load P, and with a distance A and B separated by a distance. So here you remember that the reactions that we get at these 2 points, my RA. Suppose if this is my point A and this is my point B, and where the load is acting is C, the load P. So RA is PB by L, and RB equals to PA by L over here. So let us draw 2 beams again for the shear force diagram and the bending moment diagram. So I'm going to draw my shear force diagram on this one and bending moment diagram of this one, right? So now this is the case where you do not have that uniformly distributed load, but you have a point load. And if you remember that from the different relationships which we had looked at between this load, shear and moment, one of them was for the point load. Now what kind of change did it cause? Just to jog your memory. So the situation was something like this, right? You had an element where we had V, and we had V plus V1, and we had M, and we had M plus M1, and these changes were happening when you had a concentrated load P that was acting. And if you remember, so this was a part of the relationship number 3. So what did we see in this? We had seen, and we are not going to go ahead and derive it, that your shear undergoes a jump. So V undergoes a jump, and in this case what we had was this V1. This jump means the abrupt change, right? So here you had a V, here you have a V plus, but in addition to this we have a V1 over here. So and this V1 was came out to be as minus P, which is like in the direction of the load that is there. So you have a further reduction that is there, because reduction is downward, because you're drawing the shear force in the top half, bottom half. So whatever is going down keeps going down, right? And also the moment M1 was your 0, so there was no appreciable change in moment. So it was M and M over here. So let's use this relationship to find to draw the shear force and the bending moment diagram, and we are going to make use of the other relationships as well. So here let's first draw the shear force diagram. So at the left end I do not have any option but to have this vertical reaction of PB divided by L over here. So let's just go ahead and draw that. So here I have a positive PB divided by L going up, right? Now remember that again, so think of the relationships. The one relationship is that dV dx is minus of W times x distributed load. Here you do not have any distributed load. So here the distributed load is essentially 0. So your your V is going to be a constant line, because the derivative of the constant is 0. So the V is going to be a constant up to the point of discontinuity here, that is P. So up to that particular point you're going to have a constant value up to this line C. Let me draw the guidelines again so that we are drawing neat shear force diagrams and bending moment diagrams, right? So up to this particular point, up to this point C, so this is my A and this is my B and this is my C over here. Up to this particular sorry, wrote that in the wrong order. A, B and C is over here. So up to that particular point I have this. Now here you see at P I have a point load, and when I see a point load I see the shear. So this is the positive convention for the shear. I see the shear goes a downward jump, but it reduces by a quantity of minus P. So due to this P, your additional shear that you get, V plus V1, it reduces by minus P. So here just when you go to the right hand side of P, whatever shear was there, the shear just to the right becomes V plus V1. So here already at V I had a value of PB divided by L. So it is going to be PB divided by L minus P, because V1 equals to minus P, right? So the shear right just to the right will be my PB divided by L minus P, which you see comes out as P times B minus L divided by L, which is equals to minus of PA by L, because B minus L is the total length over here. So here you are going to get a downward jump. Downward jump goes to a PA divided by L. I'm drawing on the lower half plane, so I'm not marking the negative sign over here. So from here, I do not have any other distributed load or anything. So again, I go back to this condition that it is 0. So it is going to be a constant line. So it goes as a constant. And then, of course, here you have a PA divided by L. So it goes up here, right? So here you have a positive and you have a negative. Now, this was my shear force diagram. And how is the bending moment diagram going to vary? Intuitively, I know that this is a pin and a roller, no externally applied moments over there. So I'm going to have at A and B, I'm going to have 0 bending moments. Now here at A and also the shear force is a constant, so that tells me, so let's just write that down, dm by dx equals to v. This is relationship number 2. So here your v is a constant, so that tells you your moment must be a first degree, right? And what is going to be the slope of that? The slope of that, and whether it's a positive or a negative, the slope of that will be the value of the shear at this particular point. So it is PB divided by L, and that stays constant. So you will have a constant linear line. So let's just till this point of discontinuity over here. So let's just draw that constant linear line, because I'm drawing the not constant, I'm drawing a linear line up to this particular point, because I'm dealing with this over here. Now right at this point I have a load, but I know that there is not going to be a jump in the moment. So at this point the moment stays the same. So what is the value of the moment? If I have to find the value of the moment, this is my point C over here. Now remember, I can find MC minus MA will be the area of the shear force diagram between these 2 points. So the area of the shear force is PP divided by L times this distance, which is nothing but A. So it is going to be P AB by L, and MA is 0, so MC becomes equals to, so this value over here is P AB by L. Okay. Now from here I can see that you have a 0 moment at this particular point, constant shear force. It's going to be a linearly decreasing slope over here. So easily also again, and the whole shear force or whole bending moment diagram is positive. So again, easily you could find the shear force and the bending moment diagram for this beam with a concentrated load. The next application example is for a point moment. So again, you have a simply supported beam, and exactly at the center at L over 2 you have an applied point moment of m naught over here. Now because of this m naught, you can tell that there will be 2 reactions over here. So let's just go ahead and mark the reactions at A and B. So at A, so since my direction of the moment is is clockwise over here, the reactions must develop in a way that over a distance over L, that you will have an anti-clockwise moment. So the anti-clockwise moment meaning that at this particular point at A you will have a vertically downward reaction, and here you have a vertically upward reaction. So from B to A you are going anti-clockwise, that balances your clockwise movement. And the values of the reaction will be what? Your RA will be m naught. You can easily get this by solving the equilibrium equations, but this is just by intuition. And RB will be m naught by L. I have marked the directions properly, right? So the sign doesn't matter. So RA goes vertically down, RB goes vertically up over here. Okay, now let's come over and draw the shear force diagram and the bending moment diagram. Now before we go there, remember that for a point moment, the relationships that we had looked at was that, so if you have an element where in that element, if I have a point moment m naught, and say the shear force and the bending moments, we have V M V plus V1, and m plus m1. So this was from the relationship 4, so let's just write that as well. If you are confused that we had covered these things in our previous lecture, this relationship 4, what did that tell you? That told you that when you have the point moment, your from, and you can simply derive from the equilibrium as well, that your m1 was equals to minus m naught. Now here the sign is important because here you see the applied moment was in the anti-clockwise direction over here, and because of the anti-clockwise moment, the here the jump in the moment, so this is the jump, right? So the jump in the moment was a negative m naught. So this is just important. You just have to keep in mind that that jump which I wrote, that minus m naught, was for which direction of the moment, because eventually you have to come back and deal with the beam where the moment is applied in a particular way, clockwise or anti-clockwise. And also we had seen that your v1 equals to 0, right? So no change in shear, but the jump in the moment. So let's go ahead and write the write the or draw the shear force diagram first. So we have the SFD over here. So let's just mark the guidelines again to help us draw. And one at A, one at L. So so this is my A, B, and intermediate I have C. So for the shear force diagram, I start again from the left to the right. At the left, I don't have any option but to go with a downward m naught by L, right? So here I have downward m naught by L, which is negative, right? But I'm not marking the negative since I'm drawing in the bottom half. Now, interestingly, from A to B over here, there is no other point load. There is only an intermediate moment at L over 2. But I have seen from my relationship that the shear doesn't change. So what is going to happen? This line is actually going to stay a constant throughout. So it's very interesting, this problem. So this line essentially stays a constant, which you can also probably tell from the right hand side. Here your reaction is m naught by L, so once it goes to the right, it goes up, right? So here you have the entire your shear force diagram is negative with an ordinate of m naught by L. Okay, now for the bending moment diagram, maybe I should draw the beam a little below so that it does not obstruct with what I have above. So let me draw the beam here. Now for the bending moment diagram, I have the same points. This is my A, and here I have C, I have B. Now how is the bending moment diagram going to change? Let's see. So first of all, intuition always overrides. So we have the A to B. At A it's a pin and no externally applied point moment. B it's a roller, no externally applied point moment, so we'll have a 0 moment here and a 0 moment here. Now let's follow the relationship between the, because the moment we are going to the moment from the shear diagram. So for the shear diagram is here already. So for the moment, I know my relationship is dm dx equals to your v, right? And here I have a point of discontinuity in the moment at the point C. So let's just see before that, or in this case it doesn't matter, before or after, your shear force diagram is a constant, it is a straight line, so it is a 0. So that tells me my moment must be a degree 1, right? So that means it must be linear. So you have a linear line. So the linear line, I'm going to start with A, and what is going to be the, is it going to be, you know, below or above? It is going to be below, because here you see the slope of the dm dx at x equals to 0, that is at A, equals to the value of the shear, and the value of the shear is this negative minus m naught by L. So it is going to be, you know, a downward line. So and that since it's a 0 degrees, it's going to be a linear line. So let me draw the moment over here. It goes from here to here. Now just to the left of this point C, what is the value of this moment? So let's just try to find that mc minus ma must be the area of the shear force diagram between C and A, that is negative of m naught by L times, you know, this particular distance, that is L over 2. So that is minus of m naught over 2. So here the value is minus of m naught over 2. Now what happens at the point C? At the point C, I have a concentrated moment, which is, you know, a local moment, clockwise m naught. And what did we see from this relationship over here? That whatever was the moment, it changed with m plus m1, where m1 came out to be minus, you know, this applied moment over here minus m naught, but this was in the counterclockwise direction. So let's just follow the similar rule. So just to the right of C, so maybe let's just explicitly write it. So just to the right of C, what do we get? Our m plus m1. I'm just using this terminology over here, that m plus m1 will be, what is m? M was just to the left of the moment, so that is minus m over 2 over here in this particular. So minus m naught over 2 plus m1, when this moment was, you know, being applied like this anti-clockwise, m1 came out to be minus m naught. Here the moment is applied clockwise, so m1 will be plus m naught, plus m naught. So that is nothing but m naught over 2. So you see there you are having a positive jump. So from here this guy actually goes up, right? Goes up to the point of a value of a positive m naught over 2. Now after that, you know, it is going to be 0 over here, and it is going to be a linear variation because the shear force is constant. So this diagram has a negative part over here and a positive over here. And here your convention, I do not mark this thing because I'm already drawing in the lower half plane, so I will. Yes, so I hope this problem was clear, where we used a concentrated moment to draw the bending moment diagram. This is the top one was my shear force diagram. This is my bending moment. We are going to look at one last application example, and this example will have all the possible loads, like it has a point load, it has a distributed load, it has a concentrated moment, and we'll try to solve this problem using the relationships which we had just derived. And if you remember, we had looked at this